Again, good morning. Thank you for being here. My name is Andrew Isaacs, and yes, I teach the courses on climate change here at the Haas School of Business and beyond. I limit my subject area to the subject area that I understand best, which is planet Earth, its chemistry, its biology, its evolution, and what our impacts are, and what our impacts could be potentially reduced to, and what climate change actually means. Now, in the board up here, it says a science-led approach. I am a scientist. I started my career at NASA. It is lonely work being a scientist in a business school. I'm the only one, as far as I haven't been here 25 years. I haven't met another one. Yet climate change is something that is best described through the lens of science, and that's what we're going to do a little bit this morning. Now, the formal courses that I teach take a couple different forms. These are the two that I teach most frequently, a 3-unit course, that means 3 credits, called Climate Change and Business Strategy. That's the one that JP took a few years ago. I teach that both spring and fall semesters, and also there's an online version of it now. I teach that's really, the 3-unit course is for business students who understand that climate change is redefining the economy, redefining the business activity, what commercial transactions are going to look like going forward. I also teach a 1-unit version of it, fall only. It's coming up in a couple of weeks. Both of these courses typically sell out. This one always sells out, just means all the seats are full. This is for students who have sort of a passing interest in climate change. I also teach pop-up courses that are between 1 and 3 hours, similar to this one, for people who are ever so slightly interested in climate change. And I tell students when they arrive in orientation that if you're not interested in climate change, avoid me, because that's all we're going to talk about. Here's what this morning's program looks like. We have part 1, which is what we're going to dive into right now, which is what's actually going on with the climate. There is no happy news there, none. It's varying degrees of troubling. It's probably the best way I can put it. And the reason for that was explained to me by one of my professors, who put it quite simply, that if you look at any ecosystem that exists on Earth, it is already in equilibrium with all of the inputs, things like sunlight and the composition of the atmosphere and so on. If you tinker with that ecosystem, it cannot be improved. It can only be damaged in some way. And so by altering the planet's atmosphere, which is what we're doing right now, there's no good news. There's nothing happy that comes from that. Try as we may to find happy things. There is some happiness that you'll find in part 2, which is what are the steps that we can take? And it's the reason that I'm an optimist about this topic of climate change, because as humans, we have agency. Funny thing. We can take actions based on what we observe. And the more that we observe the issue of climate change, I suspect, the more likely we are going to be motivated to take the actions necessary to deal with it. So that's just a heads up for you. Don't expect, like, as we go through these slides, that they'll be like, okay, then there's this thing and you see it's all okay. There isn't any happy news in that first part. And as JP said, we're going to go to Q&A after that. So here we go. Here's Earth and our nearest neighbor, the Moon. They're not actually this close together, just so you know. If the Earth were this big, the Moon would be about this far away. But for the purpose of making a slide, you have to put them close together. As moons go, Earth's moon is pretty big. As planets go, our Earth is pretty small. That turns out to be where the whole issue of climate change begins. And you can actually see the problem just in this image. The moon, although it's pretty big as moons go, is still not big enough to have an atmosphere. There's no atmosphere on the moon. It's not like there's a thin atmosphere. There's no atmosphere. And the reason is that the moon is just not massive enough to hold light gases That's what we call an atmosphere to the planet. If a molecule of oxygen drifts past the moon, it just keeps on going. There is not enough gravity on the moon to hold an atmosphere. Now, Earth is small as planets go, and so we have a very thin atmosphere. If we were a bigger planet, I would be out of a job because climate change wouldn't be an issue. But because we live on a pretty small planet and don't have much of an atmosphere, it's very easy to change the composition of that atmosphere. And when I say that Earth has a thin atmosphere, I mean that in both senses of the word thin. Thin as in it's not very tall. As you will discover if you ever climb a mountain, you are going up through the atmosphere and you suddenly feel in worse physical shape at the top of the mountain than you were that morning because you've actually gone up to where the air is thinner. Earth's atmosphere is thin also in the sense that it's not very dense. If you stick your hand out of your car while you're driving, the air doesn't tear your arm off. But the pressure that you feel are gas molecules in the atmosphere pushing against your hand, that light pressure, even at 60 miles an hour. It's not much. So we don't have much of an atmosphere on our planet, which makes it easy to alter the composition. Here's those two same objects looking edge on, and you can see what I was just referring to. The moon, it's not your imagination. It's a sharp horizon with the blackness of space. Earth, there's some cloud tops and a thin kind of turquoise layer. That's most of our atmosphere, a darker blue layer, and then the black of space. There's just not much atmosphere on our planet. When you stand on the surface of our planet and look up, as we're doing here in beautiful Northern California, you see the sun light passing through our atmosphere. It's that thin. Some clouds, the blue of the sky from the scattering of sunlight. Sort of a normal, unremarkable view of our atmosphere, which is made up of these three gases, nitrogen, oxygen, and argon, about 99% of what you're breathing. In fact, exactly, a little bit more than 99% of what you're breathing right now is that. About 21% oxygen, about 1% argon, and the rest of it's nitrogen. You breathe that in all day long. You have a close relationship with oxygen. You care about that a lot. It's probably your favorite element. It should be if it's not. The other two don't interact with you. You breathe in and out the nitrogen and argon, and they don't notice you, and you don't notice them. These gases are transparent, colorless, and odorless. And that's why you can see through the sky. Check it out. Tonight, if you go out, you'll see stars. Those are very far away suns that the light comes right through our atmosphere. If our atmosphere was thicker, you wouldn't. But you do because we don't have much of an atmosphere. Now, what about that other 1%? That other 1% or so of the gases that make up our atmosphere include a handful of gases that we're going to call greenhouse gases. Carbon dioxide is the one that's the most familiar to you. Carbon dioxide, or CO2, is a greenhouse gas because it traps heat that is radiating up from the surface of the Earth and doesn't let it escape into space. So that the Earth, as a result, CO2 and some other greenhouse gases, there's about 20 or 30 of them all together, keep the Earth warmer than it would otherwise be. So the Earth warms up during the day, and it can't cool off at night as much as it would otherwise. And that effect actually is happening 24 hours a day everywhere on Earth, that the very diffuse, thin concentration of CO2 in our atmosphere and some other greenhouse gases is keeping the Earth warmer than it would otherwise be. None of this would matter, and none of it has mattered for Earth history very much until very recently. And here's why. Starting in about the 1950s or so, we started to burn a lot of coal, oil, and natural gas. And that's what this chart is showing us. By the way, if you're interested in these slides, my email will be at the end. I'm happy to send you a PDF of these slides. And on each slide, you'll find where the source of the data. It's a little pro tip here. If you ever find yourself teaching climate change, show where you got your data. It's a controversial enough subject that it's like, hey, you don't have to trust me. This would be the International Energy Agency and so on. So you'll be able to decode where all of these slides come from. In any event, the horizontal axis, of course, is time, 1900 through to last year, 2023. The vertical axis is in emissions. This is billions of tons, gigatons, of carbon dioxide emissions coming from the burning of fossil fuels. Fossil means old, and that's all it means. And so this is burning of ancient coal, oil, and natural gas. Those are carbon-based compounds that have been in the Earth's crust for tens of millions of years that we are now rapidly digging up, burning because we want the heat to do something that we want to get done, like drive to the Safeway. So, and then releasing those gases up into the atmosphere. And because Earth's atmosphere is thin, we're able to change the composition of the atmosphere. Now, there's other greenhouse gases other than CO2. We're not going to focus on them for this little short course. I'll mention them later. There's other ways of us taking CO2 out of the ground and putting it in the air, in addition to burning fossil fuels. But the elephant in the room is the burning of fossil fuels producing CO2. That accounts for about 2/3 of climate change. All the other greenhouse gases combined account for about 1/3 of the climate forcing that's happening. All right, so you'll notice that right up through into about maybe 1950s or so, through World War II, we weren't actually burning a lot of coal, oil, and natural gas. Hard to believe, but the first half of the 20th century did not involve a lot of burning of fossil fuels. It was the rise of a large middle class in the United States, Japan, Canada, Europe, and later in China. That's what this last leg is here. That has given rise to enormous demand for fossil fuels. The industrial era that began as a result of abundant, cheap fossil fuels, it's by itself isn't the issue. What is the issue is the rapid expansion of a society that has decided we're going to use fossil fuels for all sorts of things. So there you have it. You'll see little down dips every now and then. That's COVID right there. That was it. Not much. Right? The economy shut down March and April mostly of 2020, and you probably saw, it's great progress was made. Yeah, that year great progress was made, if you call that progress. But we've since gone right ahead and eclipsed that down dip. That down dip is the financial crisis of 2008, 2009. When the economy slows down, which it tends to in recessions, it's what a recession is, there'll be a little bit less economic activity. It's marginally so. This isn't like COVID took us to zero or something like that. It was just a small little down dip, okay? Now, as you might imagine, if you're putting more and more billions of tons, we're now up to shy of 40 billion tons of CO2 into the atmosphere, it would be nice if it was going away somehow. It isn't. There's no, I don't know what, closet that you can throw your dirty clothes into, close the doors, and forget about it. There's nothing like that in the Earth system. CO2, carbon dioxide, is a very stable gas. It has no half-life. It doesn't break down on its own. It hardly reacts with anything at all. It's very stable. It essentially has an infinitely long half-life. The oceans take up about 1/4 of our emissions. Yay, oceans. But they're only doing it temporarily. It's not going away. It's not forming limestone that then settles to the bottom of the oceans. It's dissolving into the oceans as a gas. So yay, oceans. Thank you for temporarily, at least, taking up some of our emissions. And also green plants, as you know, photosynthesize. They take up CO2 from the atmosphere. That's what photosynthesis is. And form all of the tissues of any green plant will be made entirely from carbon out of the atmosphere. Plants do not take carbon out of the ground. They take it out of the atmosphere in the form of CO2 and make starches and sugars and lignins and cellulose and all the things that plants are made out of. Plants are taking up some CO2, but it's very hard to measure. It's somewhere between 0 and 25% of our emissions are being taken up by plants. Last year was 0, but it could be, in certain conditions, more. All right, so all of this said, we're putting more CO2 into the air. The oceans are taking up about a quarter of it. Green plants are taking up some percentage. We don't exactly know how much. But we can measure CO2 in the Earth's atmosphere directly. We started doing that in 1958. A professor at UC San Diego named Charles David Keeling began making measurements. He chose to move his laboratory from La Jolla, California, to Mauna Loa in Hawaii. I can only imagine what the grant reviewer thought when he said, well, like, La Jolla's not nice enough for you. The problem was he was trying to get away from cities, and so a good place to do that is up on top of one of the giant shield volcanoes in the Big Island of Hawaii, and that Mauna Loa is the one that they chose, and that lab is still operating there. So this is from 1958 through to a few days ago. I just downloaded these data. The concentration of CO2 in our atmosphere. Remember, it's a thin atmosphere. We're adding all this CO2. The oceans are taking up some and the trees a little bit more, but most of it's just accumulating in the atmosphere, and that's exactly what this chart shows us. The annual squiggles, you already know what that is. Plants take up CO2 in the summer. What do you think they do with it in the winter? When the leaves fall off trees and grasses die, microbes consume that plant material and CO2 goes right back into the atmosphere. This is called an equilibrium. So nature's been doing this squiggle thing for as long as there's been green plants on our planet, which is a few 100 million years. It's a long time. But this rise that you see in the Keeling curve, the concentration of CO2, that's us. That goes directly back to that slide of a minute ago. We burn more fossil fuels. This is what's actually accumulating in the atmosphere. It's going up about 3 to 4 parts per million every year. Now, ppm doesn't seem like much. It just seems like, well, that can't be bad. But don't drink water that has 1 part per billion benzene in it or 1 part per trillion arsenic. Depending on how active the chemical is, in the context, this is me as a chemist speaking now, depending on what it is we're talking about, a part per million can be a lot. So this accumulation of CO2 in Earth's atmosphere is much of what's driving the change that we're having in the climate. There's another thing you'll notice after looking at this for a minute is not just the squiggles, which is easy to explain. That's summer, winter, summer, winter, summer, winter. Plants growing, plants dying, plants growing, plants dying. And the main trend, which is that it's going up, but it's also, you start to notice that you can't draw a straight line. They tried this back in the 1960s and said, oh, okay, our emissions from cars and airplanes and power plants burning coal is increasing CO2 in the atmosphere, no surprise, but what you quickly notice is it's not a straight line. It's concave up, meaning that the accumulation of CO2 in the atmosphere is accelerating. The rate is not constant. It's getting faster. My students will look at this and say, that's an exponential. And I'll say, we'll come back in 500 years and we can determine if that's an exponential curve or not. Don't worry if it's an exponential or not. It's curving up. It's accelerating. If I try to draw another straight line, more recently, say through the 1990s, 2000s, I have the same problem. We're continuing this acceleration like this. Remember when I said there's no good news? What that means is that there is bad news. So here's some more bad news that goes with this. There's 3 possible explanations why CO2 is accumulating faster and faster in the atmosphere. Possible explanation number 1 turns out to be true, which is we're burning more gasoline, more diesel fuel, more coal, more natural gas. Okay? And we are, and that's one of the reasons. The second reason this could be happening is because, remember the oceans, yay oceans, are taking up CO2? Well, you know, we're warming the planet, and when you warm up a liquid, it can absorb less gas. It's that simple. That's called Henry's Law. If you remember that from high school chemistry class, that's all that is. And so the oceans are less able to absorb more CO2 out of the atmosphere. Damn. So it was yay oceans until we started heating them up. They're not doing the job they used to do. That's also happening. Possible explanation number 3 appears to also be happening. In fact, is also happening, which is that we have triggered some knock-on effects in Earth's ecosystems, in particular the melting of permafrost, which releases CO2. When you warm up a planet, don't expect everything to stay the same. Do expect many things to change. And so by warming up permafrost, and some other things as well, we're releasing CO2 into the atmosphere. This is sometimes called a positive feedback loop. Positive doesn't mean happy. Positive means self-reinforcing. Okay? So all of this is happening. And let's see what else is going on. Well, the most obvious effect of global warming is that we're warming the globe. This is the most recent data on this. This is looking at a 12-month period. I no longer do calendar years because things are changing fast enough that I go like this, last September to this August. I haven't quite gotten to the point where it's like this week's climate news, but you could. So looking at a 12-month period from last September to this August, this is the most recent portrayal of climate data in this way. This is averaging tens of thousands of weather monitoring stations around the globe, more than 4,000 just in the oceans. I don't know if you know that we have lots of floats that monitor ocean temperature and air temperature at the surface of the ocean. We do. So this is the effect of global warming as it is right now. There's some important things you can note about this. Number one is it's not homogeneous. It's not the same everywhere. And that's quite obvious. There's areas that have heated up quite a bit. These reddish and orangish colors relative to the mid-20th century, that's our benchmark. We're showing warming now compared with a period in the mid-20th century that we're going to call our baseline. So it's uneven heating. Number two is that the continents are heating up faster than the oceans. No surprise, we knew that would happen, and it's now happening. The reason for it is that the oceans are made of water. Water is very conductive of heat, and so the heating up of the planet in the oceans means the oceans are able to stuff heat downward through conduction. And the other reason is that oceans mix. And so the oceans are taking up quite a bit of heat, but the sea surface, in spite of what we're seeing with hurricanes, is not as bad as it would be otherwise. The land is heating up more. You'll notice that, like in South America, it looks like you took an orange crayon and colored it in. It's even more apparent if you look at the Arabian Peninsula. The Persian Gulf and the Red Sea really make the Arabian Peninsula stand out. That's all that's going on, is land heats up faster than the oceans. There are a couple of other interesting things. There's the remnants of El Nino right there. That's the heating of the equatorial Pacific, we call El Nino. You'll notice that the high latitudes are heating up faster. That's because snow melts earlier in the spring now, exposing dark land. And so that Arctic amplification effect is quite pronounced in northern Canada. There's nobody up there, but it does affect the weather of the whole planet. You'll see a stretch of blue here off of Greenland, between Greenland and Iceland. That's the melting of the ice sheet on Greenland. It's cold water coming off the top of that ice sheet, cooling the North Atlantic. And in case that wasn't enough, notice that India is anomalously cool compared with the rest of Asia. And the reason for that is that India burns a lot of coal to make electricity, and the ash and soot from that coal forms a reflective blanket over the Indian subcontinent. Sunlight is reflected away and actually cools that region. Same thing happens with volcanic eruptions. Volcanic eruptions actually cool the planet briefly. But then the ash from a volcano settles out. In the case of India, they keep burning coal, and so there's essentially a permanent ash cloud that's acting like a parasol, an umbrella over India. Okay. Here's what it looks like if you track all of the planet's temperatures, starting in January of 1850, right through August of 2024. The color codes simply show that, yeah, it heats up in the summer and it cools down as we go into fall and winter, and it's been doing that every year. Every year, no surprise, but you can tell from the color shading that as we move closer and closer to the present, there's bigger gaps between the lines, especially the last couple of years. 2023 and 2024 are much warmer than what we've had in the past. That's quite apparent. So there's no, it's not your imagination that that we just had two, what were they, the 1,000-year hurricanes, in two of them in 2 weeks. It's $100 billion in damage. Hurricanes aren't happening more often, but they're more powerful because hurricanes and typhoons get their energy from this warmer sea surface. So I'm sure you've been following the news the past couple of weeks. Next year probably will be similar for that reason. If you simply take the average of each one of those colorful lines and plot it out, here's what it looks like. 12-month moving temperature on Earth, and you can see that things have really jumped up. We're up in the sort of rolling average, 12-month moving average. We're up 1.5 degrees Celsius. That's about 3 degrees Fahrenheit warmer than we were back here in the mid-1800s. Okay. I think I'll skip this temperature plot only to point out this is, instead of lines, we're simply putting a dot for each of Earth's years. This is NASA data from 1880. And we simply have the zero temperature line running through here so that we could reference temperature increases since then. Global warming really didn't happen until about the 1960s. Maybe you could take it back to the 1930s, perhaps. But it continued. Your brain wants to draw a straight line through the data. Everybody does. That's how brains work. When we added this next 16 years, lots of people got out their straight edges, and we would like to, although heating up of the planet is not a good thing, it makes it easy to guess where is it going to be going from here. Unfortunately, in addition to CO2 in the atmosphere curving upwards, the heating is now also. That's what it appears to be. And this makes sense. Most climate models say that there's a latency, a delay, a lag between greenhouse gas accumulation and heating of about 30 to 50 years. And so the heating that we're getting right now, 2024, is due to emissions of a few decades ago. When JP said the best time to plant a tree is 20 years ago, yes, maybe 40 years ago even. But the time to take action on climate is soonish. Here, by the way, is last year. Gapped way the hell up. And here it is, we're halfway through 2024. We're still trying to figure out exactly why that happened. It's real. It's not like all the thermometers suddenly started lying or malfunctioning or something like that. These data, again, are as real as it gets. What the trend is that it seems that when we have an El Nino event, which is a heat upwelling in the Pacific, that it knocks the baseline up, and then every time we have one of these, it's like a ratchet that only goes one way. You don't come back from it. And this shows up a few times. That was a big El Nino year, 1998. We had a big El Nino year. I think this was 2016. I'm not sure. Clearly, this is a big El Nino year last year. 2024 will be about the same as 2023. So it's about as real as it gets. Okay. I'll just point out that we have data that go back tens of thousands of years. This is CO2 in the Earth's atmosphere, going back to 10,000 years ago. That's the Neolithic era, Stone Age. Metallurgy was still 5,000 years in the future. Humans were just starting to do the thing we today call farming. There were no cities to speak of. we were hunters and gatherers. So this is all of human civilization, 10,000 years. And if you look at CO2, you can see that, okay, we really started in the mid 20th century to alter the composition of the atmosphere. And a little geology corner here, we can actually go back about 1 million years. What you see here now are the ice ages. Warming, cooling, warming, cooling, warming, cooling, warming, and now this. Okay? And we also know how many degrees temperature swing this is between an ice sheet expanding and a melting and an ice sheet expanding, contracting, because that's what happens during ice ages. Ice sheets come and go in a very systematic way. That's about 8 degrees Celsius of cooling, 8 degrees Celsius warming, 8 degrees cooling, 8 degrees warming. So how much warming would you say this is? 1.5 degrees? That's what the Paris Agreement says. I'm unimpressed. In any event, we have triggered a massive heating event, and we're just starting to feel it. Again, now would be a good time to do something about it. I will mention some of the other greenhouse gases, just for completeness. In addition to, this is showing their accumulation in the atmosphere. In addition to carbon dioxide, there is, which is this light blue, dark blue is methane. This is the same stuff as we call natural gas. The source of that is natural gas pipelines, all of which leak, and the mining of coal produces a lot of methane. Nitrous oxide is a byproduct of overuse of fertilizer for farming, nitrogen fertilizer in farming. These other ones that have the letter F in them for fluorine are all fluorinated gases that are used mainly for refrigeration. So air conditioners, freezers, and so on. And they're not all going up, but cumulatively they are. Okay, where's it coming from? You already know the answer. Energy use, the 3/4 of the greenhouse gas emissions by sector is coming from the burning of coal, oil, and natural gas. Earlier I said it's about 2/3, 3/4. It's on that order. Other sources, mainly it's the production of food and so on. Okay, so how screwed are we? It depends what you mean by we. It depends what you mean by screwed. So we're not very screwed because we live in a rich part of a rich country in a rich time, and we have agency, and we have also the ability to make the kinds of changes that are needed. Subsistence farmers elsewhere in the world, it's not such a pretty picture. And again, it's not just our grandchildren, it's other people's grandchildren as well. And so this idea that maybe we owe something to more than just our own convenience and happiness and well-being, that's a philosophical idea. I'm a chemist, so I'm not going to dwell on things philosophical, but there is this idea, and I think it's a good one, that we are here on Earth briefly, and we might want to do things not only to improve our own lot, but maybe those of the people around us. So this is particularly a clarion call. How screwed are we? Us? We? This we? Not very. But there's actions that we take routinely that are impacting other people and their kids, not just in the future, but in fact in the present. Okay, so when do we get to the happy part? Well, the happy part of any problem is when you start doing something about the problem. There is no happy part to poverty. There's no happy part to homelessness. There's no happy part to climate change. There is, however, a reward that comes by taking action in doing something. And that's always the case. And the case for climate change as well. The happy part is when you start doing something about it. So what are those things? They fall into two categories. The first of them is mitigation. Use less fossil fuel. I have executives who say, I don't have an hour for a course. What just give me the gist of it. And I go, okay, use less fossil fuel. And they're like, that's the whole course? No, that's 4 words. But it does encapsulate What's the most important thing you can do? So, if you're going to fly to Europe on vacation, stay longer and then don't go back next year. That's a way to cut your air travel in half. It was like, you haven't sacrificed anything. You can do these things, and it's what I've been driving electric for 10 years. You know what? It's a hoot. I've had solar panels. You know, we live up in rural Napa County, as JP was saying. There's power. They turned the power off on Thursday because of this wind event. Thursday. We've been without power. Oh, no, we haven't. We have solar panels. We have batteries. The neighbors come over, and we have barbecues. It's really cool. All right. So all these things are very doable. And so use less fossil fuel, electrify everything you can. And the only thing you can't electrify is air travel. Everything else you can. It's not complicated, and in many cases will save you money. Now, the other part of mitigation is adaptation, which means climate change is happening whether we like it or not. And so that's the other thing that you can do as an individual or a city or a community. And I'd be remiss if I didn't mention that on November 5th, you actually get to vote on climate adaptation if you're registered to vote in California. That's exactly what Proposition 4 is. Now, you know that you have to read these props, right? That thick newsprint thing that comes and on and on. But take the time to do it, and I'm not going to tell you how to vote, other than that you should vote. But, you know, this happens to be a $10 billion bond issue here in California that is specifically about climate change adaptation in terms of making our water supplies more robust and doing prescribed burns in forests so that they don't burn so severely when they do catch fire. Like every proposition, it has to talk about safe drinking water. That's how props are in America now. It's going to be jobs, 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 safe drinking water, and better playgrounds for kids. It's going to be something that will get you enthusiastic about it. Not all of this particular adaptation bill is about adaptation, but a lot of it is. And this is something that I think you're going to see more and more of. When folks ask me why we went with solar and batteries a decade ago at our place, they think we're some kind of survivalists. Now they're coming, we're not. Now they're coming over for barbecues when their power goes out. There's an issue of resilience and adaptation that all of us are going to have to kind of think about a little bit. There was in the lead up to the hurricanes, there was an article in the Florida News was saying, is it safe to have an electric car in a hurricane? What if you can't charge it? Well, it's like, I don't know if you know this, but those gas pumps for your gasoline, they use electricity to lift the gas out of a tank that's below ground. If the electricity goes out, you can't get gasoline either. So we're just as a society, I think, starting to get our heads around this issue that climate change, dealing with climate change is not just use less fossil fuel, but it's also adaptation. Okay, I'm going to go ahead and close there and say thank you. And I know you haven't enjoyed this because it's talk about climate change, but I hope it's been beneficial in some way. Again, my contact information is on this slide, and so if you want, reach out to me. Happy to answer any questions you have. But let's also take a couple minutes for questions now. Fire away.
First of all, thank you so much. Can we have a microphone?
You have a runner here. She's amazing.
Super appreciate this bird's eye view of like the science over time of global warming. I'm a firm believer in like the need to do things across the board in how we live. But the one thing that I want to ask was, like, we all know that it's well documented that birth rates have been declining or reached historic lows in a lot of first world, like most developed countries, which coincidentally are the ones that contribute most to kind of global warming through kind of greenhouse emissions. What do you think is the effect over time of kind of lower populations in the likes of the United States, Japan, Western Europe, all sorts of developed countries, assuming that they're going to be smaller populations that are contributing less to kind of global warming? Like, how would that affect over time?
Yeah, it's a great question, and it's thank you. You could teach this class, dude. That was awesome. In fact, would you please? Do you know what it's like to teach this? So, there's a lot of rich countries where birth rates are declining. They're declining in China as well. So, the global population now is 8 billion people, and I think we're supposed to peak at about 10 billion or something. Although it's pretty hard to model that. It's also hard to model what the emissions are for those individuals. So the average, if you take global emissions, including all those other greenhouse gases, what we call CO2e, CO2 equivalent, and divide by the human population, the average human being today is responsible for about 6 tons of CO2e emissions, 6. In the US, it's much higher, 20, 30 is common. One trip to New York and back is about, what would that be? At least 2 tons, maybe 3. And that's like a trip to New York and back to see a Broadway show. That's all you did. But it's like you're already halfway there almost in your average emissions, which means there's lots of people that are well below you. Japan, it's only around 2 tons per person per year. It's really low because of how energy efficient society is. It's all mass transit, on and on. A lot of other reasons for it. So I would say one variable is population, which is what you asked about. The other variable is how do those people live? And this is why you're seeing in the past 6 months news about IT companies, Google, Microsoft, and others, basically putting down payments for nuclear reactors to power their data centers. This is not a small thing. There's about 7,000 data centers in the world. In the US, I believe we're building 1 a day. I mean, and that's because you're on your phone like this all the time. And you go, Instagram's not loading, damn it. It's just that we're so used to that sort of thing. And AI is just taking that in spades, increase that in spades. So again, it's how people live as much as anything. In that chart of emissions, when we started, was almost nothing in 1900. Global population was 2 billion people. So we've gone up from 2 to 8. That's a factor of 4. But this problem isn't a factor of 4 problem. It's that the emissions of each of us as an individual have grown so much. Time for one last question. I'm not going to choose. And I will stick around to chat if you aren't interested in the game.
I have a question about your lecture. You mentioned one of the solutions was electrify everything. Currently, 5%, if I'm correct, I read this, of EV vehicle adoption is about 5%. And it's stalled because the battery is not quite good enough. However, new batteries are coming, new ways of powering the vehicles like the solid-state battery is in the near future. Electrifying all cars would seem to make an impact. Can you comment on that?
I can. As an EV driver for 10 years now, I've been so I've lived it. When I first got my EV, by the way, and I parked it outside Haas, like the students, class ended, the students came out and gathered around and touched it and people don't do that anymore. But literally 10 years ago, what it was like is you'd be driving an EV and another EV driver, they'd wave to you. And now this is it's only 10 years ago, it wasn't a long time. Okay, so the new car sales in the United States are currently running about 10% are EV. And in Europe, about 20% on average. In China, 40%. And in fact, this year, their EVs plus plug-in hybrids in China is over 50%. It's 53% or something. So it's happening very fast. And the reason is prices are collapsing mainly for batteries. You are correct that battery technology is getting better year by year. And I swear 5 years from now, we could have the exact same conversation because they'll be getting better then too, the same as they are right now. An EV now, there was terrific new technology introduced just this spring that really changed battery technology a lot. You can now get more than 5 miles per kilowatt hour. And I realize that's a geeky unit, but that means it's going to cost you about 2 cents a mile to drive. So way cheaper than gasoline. And that's because batteries have gotten better at storing power in smaller spaces. So I would say the progress is happening right now. The batteries are getting better at the same time that they're getting cheaper. When JP introduced me, he said I started teaching this class in 2007. That's true. The class has changed a lot. At that time, solar panels were $10 per watt. That means that a 200-watt solar panel would cost you $2,000. All right, that was then. Today, solar panels are not $10 a watt. They're about 30 cents a watt. Why? Because we're making so much more of them, and we've just gotten better at it. That's mainly good old-fashioned learning curve. Companies have gotten more efficient at using materials, less waste, and so on. Same thing is now happening with batteries. So I didn't wait. I waited until electric cars existed before I went and got one. But if you're thinking about it now, actually prices have collapsed. If it wasn't for tariffs, they'd collapse a lot more. I don't know if you know this, but the U.S. has instituted a 100% tariff on Chinese-made electric vehicles. That went into effect this summer. In Europe, it's similar. I think it's 55% tariff on imported. Why? Because in China, you can buy for about $10,000 an electric vehicle about the size and shape of a Camry that has a range of 300 miles, all EV. It's battery electric vehicles. So they're so cheap, and what that would mean for the U.S. automaking industry would be a catastrophe. So, but these things don't last forever, and you'll see prices come down to where it won't make any sense at all to buy a car that runs on gasoline. I'm pretty optimistic about that. That could be bad for workers, I realize that, but technology's funny that way. Okay, it's noon, and I promised to close. Thank you so much for coming out today.